Hi everyone, and today we're going to talk about optimization, but unlike previously, we're going to be talking about optimization when we have vectors. So you've probably seen things like this before. We did a little bit of calculus in the last video, but if you've really looked at the notation of what people tend to write out, it looks like something like this. So you have some f, which has some values, and then I don't know if you actually remember from your calculus class, I always used to get it mixed up between df over dx or dx over df, but this is the correct way. So I'm taking the derivative of some function with respect to x. So this kind of implies a certain property, that we're taking it with respect to x. So let's say we had some function that was not only of x, but also of y. So based on the notation you've seen and kind of what I've been alluding to, you can probably assume that you can take some derivative with respect to x or some derivative with respect to y. And this probably makes a lot of sense. If you remember, we talked about this a little bit in the computer vision video. So the way people tend to write this is using this symbol here, which stands for partial. So it's not the full derivative, it's a partial derivative. So we can see here is we have the partial derivative of f with respect to x, the partial derivative of f with respect to y. The way you compute a partial derivative is you essentially just take a derivative normally, and you treat anything that is not the variable you're taking the partial with respect to as a constant. So let's say we have some f of x comma y, which is x squared plus 2y plus 3. If I was to take the partial with respect to x, I would get 2x because I would treat this 2y as a constant, and it would go to 0 when I take the derivative. And if I take the partial with respect to y, this x squared will be treated as a constant, so it'll go to 0, and I'm just left with 2. So let's look at some more complicated examples of partials. So I have my function f here, and we're going to take the partial with respect to x. So we're going to go through this step by step. So looking at the first term, what I can do is, since I'm taking the derivative with respect to x, essentially this x just goes away and I'm left with a 1. And then I can rewrite this as 2x, and then this is treated as a constant, so it goes to 0, and then I'm treating this y squared as a constant, so I'm left with 2y squared. And that's what I get down at the bottom. We can do the exact same process with the partial with respect to y, and you get out this equation here. So if you recall from the single variable case, we took our function, took the derivative, and set it equal to 0. And this made sense, because if we had some sort of parabola, and we were trying to find the minimum of it, what we were looking for is a point where it was not obvious where we should step to get to the minimum. So if we were here, we could step this direction. If we were here, we could step this direction. But if we're at the bottom, where f prime is equal to 0, there's no obvious direction for us to step to increase or decrease our function. So in the multivariable case, you have the exact same thing. But now what we need is for all variables to equal 0. Because if I just set f prime of x, which is equal to 2x, equal to 0, so x is equal to 0, I can, by changing the value of y, I can change my function value. Therefore, what makes sense is that y should equal to 0 as well, because this is the actual critical point where it's not obvious where we can increase or decrease our function by stepping in any given direction. So now we're going to take what we learned and apply it to x and Rn. So now we can take derivatives of functions with multiple values. Can we do this with vector valued functions? And the answer is quite yes. So first off, we have a couple of the standard programs that we're going to talk about. Remember, program just means optimization problem. So you can have things like linear programs, like you see here. And this represents a linear function because this is some fixed matrix A. And if you were actually to write this out, what you'd get is like x1, a11, x2, a12, and so on and so forth, writing out the entire equation. And if you'd actually look at it, what you'd see is a set of linear functions because there's no nonlinear components here. So there's also quadratic programs, which takes on this form, where we have x transpose ax. And there's also nonlinear programs, which we represent by another function like we have. So this could represent anything, any nonlinear function, and people will tend to write it this way. So next we have the Jacobian. So taking the first order partial derivatives of a vectored function. So this is a function that takes in a vector n and outputs a vector m. So we can think of this as having multiple functions that are going on at the same time. So it makes a lot of sense for us to get a matrix out, because we have to go across the entire set of functions, which is the m set of functions, and then for each m set of functions we have how the derivative changes with respect to each input, which represents the value n. So oftentimes in optimization we have a slightly different form of the Jacobian, and this is because now we're going, instead of from n to m, we just have from n to r. So we only have a single value output, so then our m-axis that we talked about earlier no longer needs to exist. All right, for an example, let's compute the gradient of this function. So I've taken it and I've written it out in the long form like we've normally seen. And what we're going to do is we're going to compute the gradient of f. And this is going to give us this function here. So now we're going to talk about distance or magnitude. So oftentimes when we have a vector space, it makes a lot of sense we want to define some distance. So you recall this, I did this earlier, where we were talking about the optimality conditions of a weak versus strong minima. What we're going to do here is take a mapping from a vector space to a non-negative real number. So Rn to R plus, and this is called the norm. You can think of this like the distance. This looks a lot like the distance formula because you have the square root of the sum of squares. This allows us to define some sort of distance between multiple vectors. So I can essentially say something about the relative magnitude of two vectors. Now we come back to our types of minima, but now we're in the vector case. So now I define some vector x, which is in x, such that the norm, denoted by these two bars, we're saying that the norm is less than some distance. So remember, d belongs to r because it is only a single value. I'm saying that the magnitude of the difference between these two vectors is bounded by this value delta, and delta must be greater than 0. So we have the exact same conditions we had before. We had weak local minima and strong local minima, which is whether or not there are values at the same level nearby or not, and then we have local versus global. So everything that we learned in the single variable case carries over very easily to the multivariable case. It just kind of blows up in complexity with a lot more numbers. So again, the first order necessary condition is the exact same. So the gradient at a critical point must be equal to 0. And this makes sense because if I was only to set one variable to the critical point, the other variables would be non-zero, and it would be very easy for me to figure out what direction I could take a step in and increase or decrease my function value based on the derivative. So we're going to look at an example here. So we're going to be finding the critical points of x1 squared plus 0.5 x2 squared plus 3x2 plus 4.5. So if we take the partial derivative with respect to x1 and x2, we get this gradient here, and then we can figure out the critical points by setting that equal to 0. So now we have this condition of the second order partial derivatives of a vector function. So this is the Hessian, and the Hessian looks a lot more complicated if we were outputting a vector, but see here, we are only outputting a scalar, so it stays a little bit simpler. And essentially what you're seeing is we're taking the second derivative with respect to each variable. So you're taking the derivative with respect to x1 and then the derivative with respect to x1 again, and you have this pattern moving across where you have this diagonal that represents taking the second derivative twice with respect to the same value, and the order does matter here. So oftentimes you'll see things denoted with this, so f sub xx, and this will come up a lot when we talk about controls. So now that we have the Hessian that represents the second derivative, remember that we have our second order necessary conditions that we can look at. But before we do that, we have to talk about something with respect to matrices. Because remember, we had that our second order necessary conditions depends on the positiveness or negativeness of our second derivative. Now our second derivative is a matrix. So what does it mean for a matrix to be positive or negative? So in this case, we have something called positive semi-definite and positive definite. So what positive definite means is essentially that it's greater than or equal to 0. So we write positive definite as this right here, with this funny looking greater than or equal to sign. And that means that x transpose ax, where x is any random vector from Rn, will be positive. So it doesn't matter what value of x I put in, it will end up being positive. Because if you remember, even with negative, if you look at x transpose x, it looks just like when you have the square of a value. So if I can say that, and this relates back to eigenvalues, but we're not going to be talking about that in this course, I can say that this matrix is positive semi-definite. So that is greater than or equal to, and I have the same condition for positive definite, where it's just strictly greater than. And there's also indefinite, which is unclear. And this is kind of where our saddle point condition comes back in. So you have positive and negative, definite and semi-definite. And the important thing to remember about that is it's just like we had in the single variable case, it's just a little bit different now because we get this matrix out rather than a single value. So then we can have the exact same second order necessary conditions. So remember, this is similar to what we had in the single case, so this is necessary and not sufficient. So if we have positive semi-definite, that means we might have a local min. We might have input vectors that give us a similar value in the neighborhood. So we cannot say that it is necessarily a min, but we can say that it is a critical point. So then we also have the sufficient conditions, which is where it's positive definite or negative definite. So this carries over exactly from the single variable case. And we also have indefinite, which represents the saddle point condition. The important thing to remember from this lecture is that first and second order necessary conditions can extend into Rn. We can talk about functions that take in vectors and output scalars or output other vectors with respect to these necessary conditions. With respect to optimization, it makes a lot of sense just to look at values where we have f takes in x, where x belongs to Rn, and f is a mapping from Rn to R, because a lot of times we have some sort of objective function which represents a scalar that kind of shows how good or bad we are. And this allows us to perform things like optimization on manifolds. So I can take in multiple values and output what is the best thing given all of these values.